All right, so the last thing we got to talk about is half-life and radioactive decay. Good news for you is that we have a table of radioactive isotopes. We've looked at it already. This is where that information will be to let you know what the half-life is. So table N, you should flip to table N in your reference packet to see what it looks like. But basically, guys, what half-life is, radioactive substance decay at a constant rate that is not dependent on any other factors such as temperature, pressure, or concentration. Again, everything we've talked about up until this point in the school year, temperature, pressure, concentration, those things have been affected by that. The rate of reaction has been. This, however, is not. These are not ordinary, normal chemical reactions that we've been talking about in this whole unit. It is impossible to predict when an unstable nucleus will decay because this is a completely random process. So just because something is unstable doesn't mean it's going to decay right away. Okay? It will eventually, but it's random as to when that isotope will. The only thing that can be determined is the number of unstable nuclei that will decay in a given time. That is our half-life, so the time it takes for half of the mass to decay. It's a very important concept in nuclear chemistry. That's basically what is driving nuclear reactions, like in nuclear reactors. All right, it's looking at the half-life and that decay and knowing how much of a sample is left in the rods to then see how much energy is left when they need to transfer and switch out those rods. No, guys, half-life varies per substance, so table N, which you have right there in your notes as well as your reference packets, is what you're going to look at. So let's take a look here at table N. I'm sorry. Table N, these are not all of the unstable nuclides. These are just the selected ones. So you guys, I don't anticipate you seeing anything else in terms of having to understand a half-life or do calculations unless it's on this list. The only other way that you could be asked something is if they gave you that information like in a reading passage. Okay? Otherwise, table N, if they're talking about a specific isotope, go look right here. So it tells you what the nuclide is, which isotope it is. It tells you the half-life. D stands for what? Days. Now, yeah, I was going to kind of go through it, guys. If you look down here at the bottom of table R, or excuse me, not table R, table N, it tells you what they are. So MS is milliseconds, seconds is S, minutes is min, H is hours, D is day, and then Y is years. Notice as you go down, your larger ones are toward the bottom, but then they're intermixed in there. Okay. Now we're going to have to do half-life. What's that? Which one?
Calcium 37. It's like one of the shortest ones.
Yeah, 175 milliseconds. So those are the selected radioisotopes, guys. Basically what you need to know is that the shorter the half-life, the less stable that isotope is. The longer the half-life, the more stable it is. Okay, so again, if it decays really quickly, it's very unstable. It wants to get stabilized very quickly. The longer it takes, like some of those that were times 10 to some power years, those are going to be pretty stable even though they do decay. All right. In your notes, here's some formulas that you can use. Now, I always show my students the formulas. If you are a formula person and you want to follow it, go ahead. It's not the way that I teach half-life. Reason it out. It's not that difficult if you just think about reasoning it out. So that's the way that I'm going to show it. Here are the formulas for fractions remaining or whatnot, but you can just figure it out if you just think about it and reason it out using basic math, okay? So here's our example. Most chromium atoms are stable, but chromium-51 is an unstable isotope with a half-life of 28 days. Okay? So if you were going to use the formula, your T, your half-life, you can get that from table N. It gives it to you right here. It's 28 days is your half-life. So it's saying what fraction of a sample will remain after 168 days. So you can use one of these formulas. I'm not going to do it that way. What do you think from your experience with half-life? What's the first thing you got to do?
Take the amount of days that it's done and divide it by the half-life.
Absolutely. So you guys have all done this before in the past? Or something similar to it maybe? Okay. Have you guys had to figure out fractions remaining? Yes. I see one person shaking head, so I'm going to go with that. All right. When you divide 168 by 28, you get 6. So we have 6 half-lives. So really, guys, to get a fraction remaining, all you have to do is you're going to take, it's a half-life, 1/2, times 1/2 times 1/2 times 1/2 times 1/2 times, you have 6 halves. Okay? So 2 times 2, or 2 6 factorial, all right, is all, you're not factorial, that's the wrong term. 2 6 squared, 2 to the 6th power, that's what it would be. 1/2 to the 6th power. Same thing, 1 over 2 is what I meant by that. 1 over 2 raised to the 6th. When you do that, what do you get then for your fraction remaining?
164.
There's your fraction. It's not super complex, especially if you guys have done this. This is going to be very, very easy for you. Okay? Now, that's one type of question that you could be asked for. It B. The sample of chromium-51 has an original mass of 52 grams. What mass will remain after that? How do we solve this? Take your 52, multiply it by 1/64. So you can just divide it by 64, multiply 1 over 64, same thing. 52 times 1/64, what do you get? 0.813, and that is the correct number of sig figs right there. Now, if you didn't already have the fraction that was remaining, guys, all you got to do is just figure out again how many half-lives you had. We had 6 of those, so we could just take 52 divided by 2. All right, that's going to be 26. Divide that by 2 equals 13. Divide that by 2 equals 6.5. Divide that by 2, okay? You just keep dividing by 2 depending on how many half-lives you have. Either way, you're going to get the same answer. So if you want to use a formula, be my guest, memorize these, use them, or just reason it out. That's the way that I try to get my students every year to do that. Okay? So it says in letter C, how much was present originally in a sample if chromium-51, if 0.75 milligrams remains after 168 days. Now, milligrams. We want to figure out how many grams were original there. Okay? So, how many half-lives did we have in 168 days? Okay? We had 6. So what can we start doing? You could flip your fraction if you wanted to, or just start multiplying by 2, 6, and then do that 6 times. So 0.75 milligrams. Now, if you do it in milligrams, guys, your final answer will be in milligrams. If you convert it to grams, it'll be in grams. Depending on if this is a multiple choice problem or a short answer, whatever the unit they're asking you for, that's what you have to refer to. So, since this doesn't give us a specific unit, I'm going to leave it in milligrams. All right, so 0.75 milligrams multiplied by 2. 1.5 milligrams multiplied by 2. You can continue to do that 6 times because you know how many half-lives you had. Okay? All right. What's that? Equals 3 times 2 equals 6 times 2 equals 12. What's that? 1, 2, 3, 4 times 2 equals 24 times 2 equals 48 like we had. Or, guys, if you just take 0.75 milligrams, multiply by the inverse of your fraction you had, 64, it's going to get you the same answer. Whatever way you're more comfortable with, that's what I want you guys to go with. All right? Any questions?